Hello everyone. In this lecture we are going to study the automatic transmissions and the transaxles. An automatic transmission or transaxle selects gear ratios according to engine speed, powertrain load, vehicle speed, and other operating factors. Little effort is needed on the part of the driver because both upshifts and downshifts occur automatically. A driver-operated clutch is not needed to change gears, and the vehicle can be brought to a stop without shifting to neutral. The driver can also manually select a lower forward gear, reverse, neutral, or park. Depending on the forward range selected, the transmission can provide engine braking during deceleration. The number of available forward gears in current vehicles varies from 4 to 8. Some have 0 fixed ratios and use constantly variable design where the ratio changes according to conditions. Most early automatic transmissions were 3 or 4 speed units. Today, the most common are 5 and 6 speed units. Until recently, all automatic transmissions were controlled by hydraulics only. However, most systems now feature computer-controlled operation of the torque converter and the transmission, based on input data supplied by electronic sensors and switches. The computer sets the torque converter's operating mode, controls the transmission shifting sequence, and in some cases regulates transmission oil pressure. And let's start with the first part of the automatic transmission, which is the torque converter. Automatic transmissions use a fluid clutch known as a torque converter to transfer engine torque from the engine to the transmission. The torque converter operates through a hydraulic force provided by automatic transmission fluid, often simply called transmission oil. The torque converter changes or multiplies the twisting motion of the engine crankshaft and directs it through the transmission. The torque converter automatically engages and disengages power from the engine to the transmission in relation to engine RPM. With the engine running at the correct idle speed, there is not enough fluid flow for power transfer through the torque converter. As engine speed is increased, the added fluid flow creates sufficient force to transmit engine power through the torque converter assembly to the transmission. And let's discuss right now the design of the torque converters. Torque converters are one piece. They are located between the engine and the transmission and are sealed, donut-shaped units that are always filled with automatic transmission fluid. All of the vital parts of a torque converter are housed within its shell. A flex or drive plate is used to mount the torque converter to the crankshaft. The flex plate transfers the rotation of the crankshaft to the shell of the torque converter. The flex plate is designed to flex in response to the slight change in torque converter size as pressure builds in it. It's bolted to flange on the rear of the crankshaft and mounting pads on the front of the torque converter shell. A heavy flywheel is not needed because the mass of the torque converter and the flex plate work like a flywheel to smooth out the intermittent power strokes of the engine. The flex plate or torque converter is surrounded by the ring gear for the starting motor. And let's move to the components. A standard torque converter consists of 3 elements: the pump assembly, often called an impeller, the stator assembly, and the turbine. The impeller assembly is the input member. It receives power from the engine. The turbine is the output driven member. It's splined to the transmission turbine shaft, and the stator assembly is the reaction member or torque multiplier. The stator is supported on a one-way clutch, which operates as an overrunning clutch and permits the stator to rotate freely in one direction and lock up in the opposite direction. The exterior of the torque converter shield is shaped like two balls standing on end facing each other. To support the weight of the torque converter, a short, stubby shaft projects forward from the front of the torque converter shell and fits into a pocket at the rear of the crankshaft. At the rear of many torque converter shells is a hollow hub with notches or flats at one end. Ground 180 degrees apart, this hub is called the pump drive hub. The notches or flats drive the transmission pump assembly. At the front of the transmission within the pump housing is a pump bushing that supports the pump drive hub and provides rear support for the torque converter assembly. Some other transaxles have separate shaft to drive the pump. The impeller forms one internal section of the torque converter shield and has numerous curved blades that rotates as a unit with a shield. It turns at engine speed, acting like a pump to start the transmission oil circulating within the torque converter shield. While the impeller is positioned with its back facing the transmission housing, the turbine is positioned with its back to the engine. The curved blades of the turbine face the impeller assembly, and the turbine blades have a greater curve than the impeller blades, which helps eliminate oil turbulence between the turbine and impeller blades that would slow impeller speed and reduce the converter's efficiency. The stator is located between the impeller and turbine. It redirects the oil flow from the turbine back into the impeller in the direction of impeller rotation with minimal loss of speed or force. The side of the stator blade with the inward curve is the concave side. The side with an outward curve is the convex side. And let's study right now the basic operation of torque converters. The transmission oil is used as a medium to transfer energy in the torque converters. If we take a look at the figure A, illustrates the torque converter impeller or pump at rest. Figure B shows it being driven. As the pump impeller rotates, centrifugal force throws the oil outward and upward due to the curved shape of the impeller housing. The faster the impeller rotates, the greater the centrifugal force becomes. In a figure B, the oil is simply flying out of the housing and is not producing any work. To harness some of this energy, the turbine assembly is mounted on top of the impeller. As we can see here in figure C, now the oil is thrown outward and upward from the impeller strikes the curved vanes of the turbine, causing the turbine to rotate. An oil pump driven by the converter shell and the engine continually delivers oil under pressure into the torque converter through a hollow shaft at the center axis of the rotating torque converter assembly. A seal prevents the loss of fluid from the system, so the turbine shaft is located within the shaft. As mentioned earlier, the turbine shaft is splinted to the turbine and transfer power from the torque converter to the transmission's main drive shaft. Oil leaving the turbine is directed out of the torque converter to an external oil cooler and then to the transmission's oil sump or pan. With the transmission in gear and the engine at idle, the vehicle can be held stationary by applying the brakes. At idle, engine speed is slow. Since the impeller is driven by engine speed, it turns slowly, creating little centrifugal force within the torque converter. Therefore, a little or no power is transferred to the transmission. When the throttles is open, engine speed, impeller speed, and the amount of centrifugal force generated in the torque converter increases dramatically. Oil is then directed against the turbine blades, which transfer power to the turbine shaft and the transmission. There are two types of oil flow inside the torque converters: the rotary and vortex flow. Rotary oil flow is the oil flow around the circumference of the torque converter caused by the rotation of the torque converter on its axis. The vortex oil flow is the oil flow occurring from the impeller to the turbine and back to the impeller at a 90-degree angle from engine rotation. If we take a look at the figure here, it shows the oil flow patterns as the speed of the turbine approaches the speed of the impeller. This is known as the coupling point. The turbine and the impeller are running at essentially the same speed. They can't run at exactly the same speed due to slippage between them. The only way they can turn at exactly the same speed is by using a lock-up clutch to mechanically tie them together. The stator mounts through its splint center hub to a mating stator shaft. The stator freewheels when the impeller and turbine reach the coupling stage. The stator redirects the oil leaving the turbine back to the impeller, which helps the impeller rotate more efficiently. Torque converter multiplication can only occur when the impeller is rotating faster than the turbine. A stator is either rotating or fixed type. Rotating stators are more efficient at higher speeds because there is less slippage when the impeller and turbine reach the coupling stage. Overrunning clutch. An overrunning clutch keeps the stator assembly from rotating when driven in one direction and permits overrunning rotation when turned in the opposite direction. Rotating stators generally use a roller-type overrunning clutch that allows the stator to freewheel rotate when the speed of the turbine and impeller reach the coupling point. The roller clutch is designed with a movable inner race, rollers, accordion springs, and outer race. Around the inside diameter of the outer race are several cam-shaped pockets. The rollers and accordion springs are located in these pockets. As the vehicle begins to move, the stator stays in its stationary or locked position because of the difference between the impeller and turbine speeds. This locking mode takes place when the inner race rotates counterclockwise. The accordion springs force the rollers up the ramps of the cam pockets into wedging contact with the inner and outer races. As the vehicle road speed increases, turbine speed increases until it approaches impeller speed. Oil exiting the turbine vanes strike the back face of the stator, causing the stator to rotate in the same direction as the turbine and the impeller. At this higher speed, clearance exists between the inner stator race and hub. The rollers at each slot of the stator are pulled around the stator hub. The stator freewheels or turns as a unit. If the vehicle slows, engine speed also slows along with the turbine speed. This decrease in turbine speed allows the oil flow to change direction. It now strikes the front face of the stator vanes, halting the turning stator and attempting to rotate it in the opposite direction. As this happens, the rollers jam between the inner race and hub, locking the stator in position. In a stationary position, the stator now redirects the oil exiting the turbine, so torque is again multiplied. Also, we have the lock-up torque converter. A lock-up torque converter eliminates the 10% slip that takes place between the impeller and turbine at the coupling stage. The engagement of a clutch between the impeller and the turbine assembly greatly improves fuel economy and reduces operational heat and engine speed. The assembly of a lockup torque converter is typically called torque converter clutch, or TCC. Through the years, many different types of TCC systems have been used. The most common design is the electronically controlled lockup piston clutch. Clutch lockup systems can also be fully mechanical, centrifugal controlled, or dependent on a viscous coupling. So we have the lockup piston clutch. The lockup piston clutch has a piston-type clutch located between the front of the turbine and the interior front face of the shell. Its main components are a piston plate and a damper assembly and the clutch friction plate. The damper assembly is made of several coil springs and is designed to transmit driving torque and absorb shock. The clutch is controlled by hydraulic valves, which are controlled by the PCM. The PCM monitors operating conditions and controls lockup according to these conditions. And let's move right now to planetary gears. Nearly all automatic transmissions rely on planetary gear sets to transfer power and multiply engine torque to the drive axle. Compound gear sets combine two simple planetary gear sets so load can be spread over a greater number of teeth for strength and also to obtain the largest number of gear ratios possible in a compact area. A simple planetary gear set consists of three parts: a sun gear, a carrier with planetary pinions mounted to it, and an internally toothed ring gear or annulus. The sun gear is located in the center of the assembly. It can be either a spur or helical gear design. It meshes with the teeth of the planetary pinion gears. Planetary pinion gears are small gears fitted into the framework called the planetary carrier. The planetary carrier can be made of cast iron, aluminum, or steel plate and is designed with a shaft for each of the planetary pinion gears. And the planetary pinion gears are called planetary pinions. And right now let's discuss how planetary gears work. Each member of a planetary gear set can spin, revolve, or be held at rest. Power transfer through a planetary gear set is only possible when one of the members is held at rest or if two of the members are locked together. Any one of the three members can be used as the driving or input member. At the same time, another member might be kept from rotating and thus becomes the reaction, held, or stationary member. The third member then becomes the driven or output member, depending on which member is the driver, which is held, and which is driven. Either a torque increase or speed increase is produced by a planetary gear set. Output direction can also be reversed through various combinations. Compound planetary gear sets. A limited number of gear ratios are available from a single planetary gear set. Gear sets can be combined to increase the number of available gear ratios. A typical automatic transmission has at least two planetary gear sets connected together to provide the various gear ratios needed to effectively move a vehicle. There are two common designs of compound gear sets: the Simpson gear set, in which two planetary gear sets share a common sun gear, and the Rovina gear set, which has two sun gears, two sets of planet gears, and a common ring gear. Many transmissions are fitted with additional single planetary gear sets connected in a tandem to provide additional forward speed ratios. And let's discuss right now the Simpson gear train. The Simpson gear retrain is an arrangement of two separate planetary gear sets with a common sun gear, two ring gears, and two planetary pinion carriers. A Simpson gear retrain is the most commonly used compound planetary gear set and is used to provide three forward gears. One half of the compound set, or one planetary unit, is referred to as the front planetary, and the other planetary unit is the rear planetary. The two planetary units do not need to be the same size or have the same number of teeth on their gears. The size and number of gear teeth determine the actual gear ratios obtained by the compound planetary gear assembly. Gear ratios and direction of rotation are the results of applying torque to one member of either planetary unit, holding at least one member of the gear set, and using another member as the output. For the most part, each automobile manufacturer uses different parts of the planetary assemblies as inputs, outputs, and reaction members. The role of the planetary members also varies with different transmission models from the same manufacturer. There are also many different apply devices used in the various transmission designs. A Simpson gear set can provide the following gear ranges: neutral, first reduction gear, second reduction gear, direct drive, and reverse. The typical power flow through a Simpson gear retrain when it's in a neutral has engine torque being delivered to the transmission's input shaft by the torque converter's turbine. No planetary gear set member is locked to the shaft. Therefore, engine torque enters the transmission but goes nowhere else. When the transmission is shifted into first gear, engine torque is again delivered into the transmission by the input shaft. The input shaft is now locked to the front planetary ring gear that turns clockwise with the shaft. The front ring gear drives the front planet gears also in a clockwise direction. The front planet gears drive the sun gear in a counterclockwise direction. The rear planet carrier is locked, therefore the sun gear spins the rear planet gears in a clockwise direction. These planet gears drive the rear ring gear, which is locked to the output shaft in a clockwise direction. The result of this power flow is a forward gear reduction. When the transmission is operating in a second gear, engine torque is again delivered into the transmission by input shaft. The input shaft is locked to the front planetary ring gear, and that turns clockwise with the shaft. The front ring gear drives the front planet gears also in a clockwise direction. The front planet gears walk around the sun gear because it's held. The walking of the planet forces the planet carriers to turn clockwise. Since the carrier is locked to the output shaft, it causes the shaft to rotate in a forward direction with some gear reduction. So when operating in third gear, the input is received by the front ring gear as in another forward positions. However, the input is also received by the sun gear. Since the sun and ring gear are rotating at the same speed and in the same direction, the front planet carrier is locked between the two and is forced to move with them. Since the front carrier is locked to the output shaft, direct drive results. To obtain suitable reverse gear in a Simpson gear train, there must be gear reduction, but in the opposite direction as the input torque. The input is received by the sun gear as the third gear position and rotates in a clockwise direction. The sun gear then drives the rear planet gears in a clockwise direction, and the rear planet carrier is held. Therefore, the planet gears drive the rear ring gear in a counterclockwise direction. The ring gear is locked to the output shaft that turns at the same speed and direction as the rear ring gear. The result is a reverse gear. Typically, when the transmission is in a neutral or park, no applied devices are engaged, allowing only the input shaft and the transmission's oil pump to turn with the engine. In park, a pole is, and we will move and discuss right now the Revino gear train. The Revino gear train, like the Simpson gear train, provides forward gears with a reduction, direct drive, overdrive, and reverse operating range. The Revino offers some advantages over Simpson gear train. It's very compact. It can carry a large amount of torque because of the great amount of tooth contact. It can also have 3 different output members. However, it has a disadvantage because it's more complex and therefore its actions are more difficult to understand. Revenue gear train is close to use 2 sun gears, one small and one large. They also have 2 sets of planetary pinion gears, 3 long pinions and 3 short pinions. The planetary pinion gears rotate on their own shaft that are fastened to common planetary carrier. A single ring gear surrounds the complete assembly. And let's discuss another type of automatic transmission, which is the continuously variable transmission, or CVT. Another unconventional transmission design, the continuously variable transmission, CVT, is a transmission with no fixed forward speeds. The gear ratio varies with engine speeds and temperature. These transmissions are, however, fitted with a 1-speed reverse gear. Some CVT transaxles do not have a torque converter. Rather, they use a manual transmission type flywheel with a start clutch instead of relying on planetary or helical gear sets to provide drive ratios. A CVT uses belts and pulleys. One pulley is the driven member and the other is the drive. Each pulley has a movable face and a fixed face. When the movable face moves, the effective diameter of the pulley changes. The change in effective diameter changes the effective pulley or gear ratio. A steel belt links the driven and drive pulleys. To achieve a low pulley ratio, high hydraulic pressure works on the movable face of the driven pulley to make it larger. In response to the high pressure, the pressure on the drive pulley is reduced. Since the belt links the 2 pulleys and the proper belt tension is critical, the drive pulley reduces just enough to keep the proper tension on the belt. The increase of pressure at the driven pulley is proportional to the decrease of pressure at the drive pulley. The opposite is true for the high pulley ratios. Low pressure causes the driven pulley to decrease in size, whereas high pressure increases the size of the drive pulley. Different speed ratios are available anytime the vehicle is moving because the size of the drive and the driven pulleys can vary greatly. Vehicle loads and speeds can be changed without changing the engine speeds. With this type of transmissions, attempts are made to keep engine operating at its most efficient speed, thus increasing fuel economy and decreasing emissions. And let's move right now to planetary gear controls. Certain parts of the planetary gear train must be held, while others must be driven to provide the needed torque multiplication and direction for vehicle operation. Planetary gear controls is the general term used to describe transmission bands, servos, and the clutches. We'll start right now with the transmission bands. A band is a braking assembly positioned around a stationary or rotating drum or a carrier. The band brings a drum to a stop by wrapping itself around the drum and holding it. The band is hydraulically applied by a servo assembly. Connected to the drum is a member of the planetary gear train. The purpose of a band is to hold the member of the planetary gear set by holding the drum and connecting a planetary gear member stationary. Bands provide excellent holding characteristics and require minimum amount of space within the transmission housing. When a band closes around a rotating drum, a wedging action takes place to stop the drum from rotating. The wedging action is known as self-energizing action. A typical band is designed to be larger in diameter than the drum it surrounds. This design promotes self-disengagement of a band from the drum when servo-apply force is decreased to less than servo-release spring tension. A friction material is bonded to the inside diameter of the band. Band lugs are either spot welded or cast as a part of the band assembly. The purpose of the lugs is to connect the band with the servo through the actuating linkage and the band anchor at the opposite end. The band's steel strap is designed with slots or holes to release fluid trapped between the drum and the applying band. Also, we have the transmission servos. The servo assembly converts hydraulic pressure into a mechanical force that applies a band to hold a drum stationary. Simple and compound servo are used to engage bands in modern transmissions. Simple servo. In a simple servo, the servo piston fits into the servo cylinder and is held in the released position by a coil spring. The piston is sealed with a rubber ring which keeps fluid pressure confined to the apply side of the servo piston. To apply a band, fluid pressure is directed to the apply side of the servo piston. The servo piston moves against the return coil spring and develops servo apply force. This force is applied to the band lug through the apply lever and strut. At the opposite end of the band is the anchor strut or end pin and adjustment screw. These hold that end of the band stationary as the band tightens around the rotating drum. This rotating drum comes to a stop and is held stationary by the band. When a servo apply force is released, the return spring forces the servo piston to move in the cylinder with the servo apply force removed. The band springs free and permits drum rotation. We have also the compound servo. A compound servo has a cylinder that casts as a part of the transmission housing. If the servo is located near the front of the transmission, it uses seal rings capable of withstanding the heat generated by the torque converter and engine. When the compound servo is applied, fluid pressure flows through the hollow piston push rod to the apply side of the servo piston. The piston compresses the servo coil spring and forces the push rod to move one end of the band toward the adjusting screw and anchor. The band tightens around the rotating drum and brings it to a stop. Fluid pressure is applied to the release side of the servo piston when the band is to be released. Let's discuss right now the transmission clutches. In contrast to a band which can only hold planetary gear member, transmission clutches are capable of both holding and driving members. So let's start with the overrunning clutches. In an automatic transmission operation, both sprag and roller overrunning clutches are used to hold or drive members of the planetary gear set. These clutches operate mechanically. An overrunning clutch allows rotation in only one direction and operates at all times. One-way overrunning clutches can be either roller type or sprag type clutches. Another type of the clutches is the multiple disc clutches. A multiple disc clutch uses a series of flat friction discs to transmit torque or apply braking force. The discs have internal teeth that are sized and shaped to mesh with the splines on the clutch assembly hub. Between each pair of friction discs is a flat steel disc. These discs have external teeth that are sized and shaped to mesh with internal splines in the transmission housing or clutch drum. The combination of friction and steel plates make up the clutch pack. The clutch pack also has one very thick plate known as the pressure plate. The pressure plate has tapes around the outside diameter to mate with the channels in the clutch drum. It's held in place by a large snap ring. Upon engagement, the clutch piston forces the clutch pack against the fixed pressure plate. And let's move right now to discuss the bearings, bushings, and the thrust washers. When a component slides over or rotates around another part, the surfaces that contact each other are called bearing surfaces. A gear rotating on a fixed shaft can have more than one bearing surface. It's supported and held in place by a shaft in a radial direction. Also, the gear tends to move along the shaft in the axial direction as it rotates and is therefore held in place by some other components. The surfaces between the sides of the gear and the other parts are bearing surfaces. So a bearing is a device placed between two bearing surfaces to reduce friction and wear. Most bearings have surfaces that either slide or roll against each other. In automatic transmission, sliding bearings are used where one or more of the following conditions prevail: low rotating speeds, very large bearing surfaces compared to the surfaces present, and low use applications. Rolling bearings are used in high-speed applications, high load with relatively small bearing surfaces, and high use. Also, we have the bushings. Our bushings are cylindrically shaped and usually held in place by a press fit. Since bushings are typically made of a soft metal, they act like a bearing and support many of the transmission rotating parts. They are also used to precisely guide the movement of various valves in the transmission's valve body. Bushing can also be used to control fluid flow. Some restrict the flow from one part to another, while others are made to direct fluid flow to a particular point or part in the transmission. Also, we have the thrust washers, normally controls free axle movement or end play. Since some end play is necessary in all transmissions because of heat expansion, proper end play is often accomplished through selective thrust washers. These thrust washers are inserted between various parts of the transmission. Whenever end play is set, it must be set to a manufacturer's specifications. Thrust washers work by filling the gap between two objects and become the primary wear item because they are made of softer materials than the parts they protect. Also, we have snap rings. Many different sizes and types of snap rings are used in today's transmissions. External and internal snap rings are used as retaining devices throughout the transmission. Internal snap rings are used to hold servo assemblies and the clutch assemblies together. Another important part in the automatic transmission is the gaskets and seals. The gaskets and seals of an automatic transmission help to contain the fluid within the transmission and prevent the fluid from leaking out of the various hydraulic circuits. Different types of seals are used in automatic transmissions. They can be made of rubber, metal, or Teflon. Transmission gaskets are made of rubber, cork, paper, synthetic material, metal, or plastic. So what is the gaskets? Gaskets are used to seal two parts together or to provide a passage for fluid flow from one part of the transmission to another. Gaskets are easily divided into two separate groups, hard and soft. Depending on their application, hard gaskets are used whenever the surfaces to be sealed are smooth. This type of gasket is usually made of paper. A common application of a hard gasket is the gaskets used to seal the valve body and oil pump against the transmission case. Hard gaskets are also often used to direct fluid flow or to seal some of passages between the valve body and the separator plates. Also, we have seals. As the valves and the transmission shafts move within the transmission, it's essential that the fluid and the pressure to be contained within its bore. Any leakage would decrease the pressure and result in poor transmission operation. Seals are used to prevent leakage around valves, shafts, and other moving parts. Rubber, metal, or Teflon materials are used throughout the transmission to provide for static and dynamic sealing. Both static and dynamic seals can provide for a positive and non-positive sealing. And let's move right now to study the hydraulic system of automatic transmission. A hydraulic system uses a liquid to perform work. In an automatic transmission, this liquid is automatic transmission fluid, ATF. ATF is one of the most complex fluid produced by the petroleum industry for the automobile. The transmission's pump is the source of all fluid flow in the hydraulic system. It provides a constant supply of fluid under pressure to operate, lubricate, and cool the transmission. Pressure regulating valves change the fluid's pressure to control the shift quality of the transmission and the shift points of the transmission equipped with a governor. Flow directing valves direct the pressurized fluid to the appropriate apply device to cause a change in gear ratios. The hydraulic system also keeps the torque converter filled with a fluid. The reservoir for ATF is the transmission's oil pan fluid is drawn from the pan and returned to it. The pressure source is the oil pump. The valve body contains control valving to regulate or restrict the pressure and the flow of fluid within the transmission. The output devices for the hydraulic systems are the servos or clutches operated by hydraulic pressure. And let's move to study the hydraulic principles. An automatic transmission uses ATF fluid pressure to control the action of the planetary gear sets. This fluid pressure is regulated and directed to change gears automatically through the use of various pressure regulators and control valves. Fluids work well in increasing force because they are perfect conductors of pressure. Fluids can't be compressed, therefore, when a piston in a cylinder moves and displaces a fluid, that fluid is distributed equally within the circuit. And let's discuss the application of hydraulics in transmissions. A common hydraulic system within an automatic transmission is the servo assembly, which is used to control the application of a band. The band must tightly hold the drum or planetary carrier it surrounds when it's applied. The holding capacity of the band is determined by the construction of the band and the pressure applied to it. This pressure or holding force is the result of the action of a servo. The servo multiplies the force through hydraulic action. And let's discuss the functions of the automatic transmission fluid, or the ATF. The ATF circulating through the transmission and torque converter and over the parts of the transmission cools the transmission. The heated fluid typically moves to a transmission fluid cooler where the heat is removed as the fluid lubricates and cools the transmission. It also cleans the parts. The dirt is carried by the fluid to a filter where the dirt is removed. Another critical job of ATF is its role in shifting gears. ATF moves under pressure throughout the transmission and causes various valves to move, and the pressure of the ATF changes with the changes in engine speed and load. ATF is also used to operate the various applied devices, clutches and bands in the transmission. At the appropriate time, a switching valve opens and sends pressurized fluid to the apply device that engages or disengages a gear. And let's move to another part, which is the reservoir. A fluid reservoir stores fluid and provides constant source of fluid for the system. In an automatic transmission, the reservoir is the pan, typically located at the bottom of the transmission case. ATF is forced out of the pan by atmospheric pressure and into the pump and is then returned to it after it has circulated through the selected circuits. A transmission dipstick placed within the filter tube is typically used to check the level of the fluid and to add ATF to the transmission. All reservoir must have an air vent that allows atmospheric pressure to force the fluid into the pump. When the pump creates a low pressure at its inlet port, the pans of many automatic transmissions vent through the handle of the dipstick. Others rely on a vent in the transmission case. Transmissions must also be vented to allow for the exhaust of build-up air pressure that result from heat and from the moving components inside the transmission. Also, let's discuss another important part, which is the transmission coolers. The removal of heat from ATF is extremely important to the durability of the transmission. Excessive heat causes the fluid to break down. Once broken down, ATF no longer lubricates well and has poor resistance to oxidation. Oxidized ATF may damage transmission seals. Also, we have another part, which is the valve body. For efficient transmission operation, the bands and multiple disc packs must be released and applied at the proper time. The valve body assembly is responsible for the control and distribution of pressurized fluid throughout the transmission. This assembly is made of 2 or 3 main parts: a valve body, a separator plate, and transfer plate. These parts are bolted as a single unit to the transmission housing. The valve body is machined from aluminum or iron and has many precisely machined bores and fluid passages. Various valves are fitted into the bores, and the passages direct fluid to various valves and other parts of the transmission. The separator and the transfer plate are designed to seal off some of these passages and to allow fluid to flow through specific passages. The purpose of a valve body is to sense and respond to engine and vehicle load, as well as to meet the needs of the driver. Valve bodies are normally fitted with 3 different types of valves: spool valves, check ball valves, and poppet valves. The purpose of these valves is to start, to stop, or to use movable parts to regulate and direct the flow of fluid throughout the transmission. Also, we have the oil pump. The source of fluid flow through the transmission is the oil pump. 3 types of oil pumps are commonly used in automatic transmissions: gear type, rotor type, and vane type. Oil pumps are driven by the pump drive hub of the torque converter or oil pump shaft and or converter cover on transaxles. Therefore, whenever the torque converter cover is rotating, the oil pump is driven and the oil pump creates fluid flow throughout the transmission. Another part we have is the pressure regulator valve. Transmission pumps are capable of creating excessive amount of pressure that may cause damage. Therefore, the transmission is equipped with a pressure regulator valve, which is normally located in the valve body. Pressure regulating valves are typically spool valves that toggle back and forth in their bores to open and close the exhaust passage. By opening the exhaust passage, the valve decreases the pressure of the fluid. As soon as the pressure decreases to a predetermined amount, the pull valve moves to close off the exhaust port and the pressure again begins to build. The action of the spool valve regulates the fluid pressure. Also, we have the governor assembly. The governor assembly is driven by the transmission's output shaft, senses road speed, and sends fluid pressure signal to the valve body to either upshift or downshift. When a vehicle speed is increased, the pressure developed by the governor is directed to the shift valve. As the speed increases, the spring tension and throttle pressure on the shaft valve are overcome and the valve moves. This action causes an upshift. Likewise, a decrease in speed results in a decrease in pressure and downshift. Also, we have the MAP sensor. Engine load can be monitored electronically through the use of various electronic sensors that send information to an electronic control unit, which in turn controls the pressure at the valve body. The most commonly used sensor is the MAP sensor. The MAP sensor senses air pressure in the intake manifold. The control unit uses this information as an indication of engine load. And if we take a look at this figure here, it shows the complete hydraulic system as used in a 4-speed automatic transmission. Note the extra shift valves. The various hydraulic system circuits must be compact and very possible means used to avoid external tubes or other awkward fluid transfer arrangements. And many of the shafts and other units are drilled to carry fluid. So this schematic shows the transmission operation with the engine running and the transmission in park.